So continuing on, we're going to be talking about different functional groups. Here we're going to be talking about ethers for just a moment. So ethers are actually relatively unreactive, so we're not going to spend a lot of time talking about them. So with ethers, we'd already talked about them a little tiny bit when we were talking about SN2 reactions. And remember, we made an ether as a functional group whenever we reacted our alkoxide ions. So if you remember, we talked about ethoxide and methoxide as a nucleophile. And if we reacted those with methyl or primary leaving groups. And with this reaction, we just want to take it a little bit further and talk about it in more details. So remember, we talked about alkoxides as being a negatively charged oxygen. So at the time, I talked about it as being a deprotonated alcohol. But we didn't talk about how do we actually deprotonate the alcohol, how do we get the hydrogen off there. And so we're going to talk about that now. So the basic reaction that we're going to be looking at here is just the reaction of an alkoxide with some electrophilic carbon. So in this case, it's going to be carbon that's attached to a leaving group, and our leaving group is a halogen. So if we react an alkoxide with a carbon group that has a halogen, we do the SN2 reaction, and we end up making an ether as a product and kicking out the leaving group. So here's an example of that. So here we have an alkoxide, negatively charged oxygen. Here we have a carbon that's attached to a halogen. So this is my nucleophile. This is my electrophilic carbon. And when we were talking about SN2 reactions, that's what happens. It's still an SN2 reaction, it's still a substitution. So we are substituting this leaving group with whatever our nucleophile is. So here all we're doing is basically whatever alkyl group is attached to our halogen will now be coming off of our oxygen, and that's going to make an ether. So this methyl group is this methyl group here. The nucleophile is connecting with the electrophilic carbon. So one of the things we haven't mentioned is this reaction is so common, they actually have a name for it. And so this is our first experience with what's called a name reaction, which is common in organic chemistry. And when we say named, it's named after the scientist who did the basic work on it. This was a long time ago. But this reaction, the reaction of an alkoxide with a halogen, is called a Williamson ether synthesis. And knowing these names is actually part of organic chemistry. So you need to know that this reaction is called a Williamson ether synthesis. It's an important part of learning organic chemistry. And this is some things that I could possibly ask on an exam. So how do we form an alkoxide? So, you know, it is a deprotonation, but we want to make it kind of a clean nucleophile, so we don't really want to react an alcohol with a base. So literally what they react it with is sodium metal. And I think we've all seen sodium metal. This is the same stuff. You throw it into water and, you know, it has a very violent reaction. But if you react sodium with an alcohol, it actually it does a reaction where it pulls the hydrogen, and we need two of these. We pull two hydrogens off of two different alcohols and then make H2, and then this forms two of our alkoxides. So it pulls the hydrogen off, makes an alkoxide, negatively charged oxygen, and the idea is really we can't have just a negatively charged oxygen. There needs to be something positively charged. In this case, the positively charged species is the sodium. So I've done this reaction multiple times. If you want to make an alkoxide, literally you just start with a solution of, say, methanol, and then you throw sodium into it, and the sodium reacts with some of the methanol. It actually fizzes, you'll see it bubble, and over time you'll make a solution of sodium alkoxide in this case. And the idea is, now that we've done the deprotonation, this oxygen is a good nucleophile. Now all we have to do is react it with a halogen to do the Williamson ether synthesis. So we talk about these things in terms of what's happening, but remember, overall what we're looking at is the reactions themselves. So understanding how do we go from reactants to product. If I give you a reactant, what does the product look like? So if I take an alcohol, so same thing, it doesn't really matter what alcohol I have. The carbons that are coming off of here doesn't really matter. The reaction is with the OH. If I react an alcohol with sodium, the H comes off, we form an alkoxide, and then we get a positively charged counterion, in this case of sodium. So if I take this alcohol and react it with sodium, I end up making an alkoxide version of this. And then the same thing, this alkoxide is now a good nucleophile, and it can go on and react with a halogen to do the Williamson ether synthesis. So the idea is, most of the time we really have no reason to form an alkoxide unless we're going to do the Williamson ether synthesis. So this is a very reactive molecule, and it's not something that we particularly want to make for a long period of time. So usually we only make an alkoxide to then subsequently do the Williamson ether synthesis. So when we look at this, a lot of the times what they will show is this reaction going in 2 steps, and I don't think we've seen this yet, where now our reactants are broken into a 1 and a 2. This means that there's actually 2 reactions going on. So to go from my reactants to my products, there are actually 2 different reactions going on, and you need to know what's going on in each one of these individual steps. And so this overall, so we start with an alcohol, we end up with an ether. We have 2 steps, a reaction with sodium and a reaction with our halogen. All this together does a Williamson ether synthesis. So you need to remember what's going on with each reaction step, but a lot of times they will put these 2 steps together, and the idea is we usually don't form an alkoxide without going on and doing the Williamson ether synthesis. So here, sodium during the first step reacts with the alcohol to make an alkoxide. In the second step, the alkoxide reacts with the halogen to do the Williamson ether synthesis, and we add the alkyl group onto the oxygen to make an ether. Overall, what's happening, and this is the way I like to think about reactions, is what do I have to do to my reactant to get it to my product in this case? When I see that I'm doing a Williamson ether synthesis, I take off the hydrogen, and then I replace it with whatever alkyl group is attached to my halogen. So here my halogen has an ethyl group, CH2, CH3 coming off of it. Well, that ethyl group is now going to be coming off of my oxygen now. So these 2 carbons here came from my halogen. So those 2 things together perform this reaction. So a couple of things we need to do. Up until now, we've been looking at reactions in terms of going forward, and we just talked about that with our ether synthesis. I react an alkoxide with a halogen. In this case, this is an iodine right here. We kick out the leaving group and we place it with the alkoxide. So this is the main type of question that I can ask with these reactions. I say, here is my reactants, and you need to come up with the product. And in this case, this is my answer. This would be the answer I would expect on an exam. So I understand that whatever alkyl group's coming off of my halogen is going to be coming off of my alkoxide now. And this is my product. So this is I call these forward reactions. Given the reactant, what's going to be the product? But as part of organic chemistry, there's more facets that we need to talk about. So next semester, we're going to get into linking these reactions together. So the idea is, why are we learning all these reactions? Well, this allows us to turn simple molecules into more complex molecules, and we'll go over that more next semester. But the idea is we need to start thinking about these reactions differently in order to understand sort of the more detailed parts of organic chemistry. So you need to start being able to think about reactions in reverse. And for right now, just learn the reactions like this, and we'll get into more why do we think about reactions in reverse. And this is the other type of question. So when I say reverse, it means I know I want to make this molecule, and then I say I have one piece as a halogen, and I need to know what's this other piece here. So I need to know what do I need to start with in order to make this reaction. So when you see this, one of the first things you want to identify is what reaction is going on. We've only talked about one reaction that makes an ether, so I must be doing our Williamson ether synthesis. I look at what I'm starting with here, and I have a halogen, so the other piece here must be an alkoxide. And more than that, I need to know, what does that alkoxide look like? So I know during this reaction, I replace my halogen with the alkoxide version, or the alkoxide piece. And so I say, really what we're doing is we're forming and putting this ring species here onto the oxygen, because it has a halogen attached to it. So my alkoxide must be this other piece. So the oxygen and these 3 carbons here must be coming from my reactant here. So when I say what piece, so what's the question mark here? It's got to be an alkoxide version. So the alkoxide, this oxygen, and these 3 carbons here. So this is the piece that I would make. So this is, one of the lesser problems. So this is what I say overall when you start learning these reactions. I'm only going to ask questions like this about reactions that we've learned since the 3rd midterm. But mainly you want to learn the forward version. So this is where you start. You say, okay, here's my reactants, what's going to be my product, learn that for all the different variations of reactions that we've been going. And once you understand those very well, that's the major type of question I'm going to ask. But I will ask some of these sort of variations here where I need to be able to think about things in reverse. So that's a minor subset. The main one is forward, but you need to start thinking about how do I look at these reactions in reverse, and then we're going to build off of this idea next semester. So the last version here is the reagent version, and by that I mean I also need to know what reagent do I need to do this conversion. So here I've given you the reactants, I've given you the products, I need to know what the reagent is here to do that. And the same thing, a lot of it is just kind of being familiar with the reactions that are going on. So here I'm forming an alkoxide. I only know one way to form an alkoxide, that's by reacting an alcohol with sodium. But this is part of organic chemistry. I need to be familiar with these reactions. I need to understand what reagent do I need to cause this conversion. So here it would be sodium would be the answer. So same thing you need for these reactions that we learned since the 3rd midterm, you need to be able to understand what reagents I might need in these individual cases. So that's about as far as we go with alkoxide. So like I said, these reactions, make sure you learn the forward ones first, then the reverse and the reagent. These are only going to apply on reactions that we've learned since the 3rd midterm, but we're going to learn other reactions, so you need to know all of them in this sort of sense. The next thing we're going to look at is double bonds. So the reactivity of double bonds is going to be a little bit different than what we'll be talking about. So we're going to be adding additions to CC multiple bonds. So we're going to talk about double bonds and then triple bonds as a functional group. So we've already kind of talked about it, and I might mention this when we talk about functional groups. We are interested in how do we make these functional groups, and then more importantly, what reactions can I do to these functional groups. So we're going to see this repeated as we go on through organic chemistry. We're going to pull up a functional group. We might talk about the nomenclature, and then we might say, well, how do I make these functional groups? And then mostly what we're going to be looking at is what's the reactivity of these functional groups and what kind of reactions can we do. So the next thing we're going to talk about is the additions to multiple bonds. So remember a double bond or a triple bond. So remember the first bond is a sigma bond, the second bond is pi, and then the third bond is a pi bond. So multiple bonds have pi bonds inside of them, and pi bonds are electron rich. So just think about double bonds and triple bonds as being, having a lot of extra electrons. And so you can kind of see that, I have more than the one line that I need to connect these things. I have more electrons that I can use for reactions. So multiple bonds can undergo electrophilic addition. So we've been talking about nucleophilic addition, and we're still not done talking about nucleophiles. But with these, because multiple bonds are electron rich, we're going to start with a reaction with an electrophile. So an electrophile is kind of the mirror image of a nucleophile. Nucleophile is negatively charged, so our electrophile is going to be something that's positive charge. Electrophile means I'm going after electrons. And for us in here, we're really going to find, at least in the beginning, most electrophiles are going to be H+. So with our reactions with multiple bonds, in the beginning, they're going to start with an electrophilic addition, and we're going to start by reacting it with H+. So what we'll also see is that we're going to look at a few different reactions, and inside of these different reactions, there's going to be a base reaction that we're going to talk about, and we're going to look at variations of this. So when we do an electrophilic addition to a double bond, there is in these general mechanisms, and so in these different reactions, there will be subtle differences in the mechanisms, but inside of all these mechanisms, we're going to see two steps. The first step is an electrophilic attack. So here, a double bond, it's electron rich. Remember, electrons attack things. So here, the electrons are going to attack our electrophile, and then we're going to add an electrophile to one of the bonds inside of our, one of the carbons inside of our double bond. And like we've talked about, we're not going to talk about the kinetics of this, but this step is going to be slow for the same reason we form a carbocation intermediate. But now we have something that's positively charged. And so in that case, when I have something that's positively charged, so just like the SN1 reaction, what's likely to happen is to have a nucleophilic attack. So we're not done talking about nucleophiles. Nucleophiles are still involved in these reactions, but we have to start with an electrophilic attack to form a carbocation. Then a nucleophile can come. The nucleophile, remember, lone pair electrons, a negative charge, will attack our carbocation, and then overall we'll add a nucleophile to the other carbon that's inside of our double bond. So you're going to hear me say this a bunch of times. Overall, with electrophilic addition, what you do is you break the double bond, so we get rid of the double bond. We're looking from reactants to products here. We're going to break the double bond and we're going to form two single bonds. So we ended up forming this carbon electrophile bond and this carbon nucleophile bond. We break the double bond, we form two single bonds, and then the question is what goes on those two single bonds. In this case, the question is what's our electrophile and what's our nucleophile. And overall, that's going to be our real variables, are what's the electrophile, what's the nucleophile, and by changing those, we can change these reactions. And you're going to see this mechanism is inside of almost all the mechanisms that we're going to talk about, and we move on from there. So overall, during this reaction, we add an electrophile and a nucleophile to our double bond. Break the double bond, form two single bonds. What goes on those two single bonds? And that's going to be the variable. But one's going to be an electrophile and one's going to be a nucleophile. And as part of this learning the reaction, you want to be able to maintain or understand what's the electrophile and what's the nucleophile in this case. So yeah, the first step is slow. We form a carbocation. The second step's fast here because we're getting rid of the carbocation. So the first reaction that we talk about is kind of classic. We add HX, and remember, X is just a generic name for halogens. And so you get like HBr or HCl. You really don't see HF so much, but it means I can have some variability in what halogen goes on. And here what we do is we have our double bond, we add HX, and you can kind of see this. You break the double bond, you add two single bonds. What goes on those single bonds? Well, one gets the halogen and the other one gets the hydrogen. So we end up adding both of these species to our double bond, a hydrogen and a halogen. But if you look at it, and this is going to be the one tricky part with electrophilic additions to double bonds, that there is a more and less substituted side on my double bond. So substituted means has anything, pretty much anything other than a hydrogen. So this carbon in my double bond has one R group. Remember, an R group just means some carbons and hydrogens. This carbon has two R groups. So this is the more substituted carbon. This is the less substituted carbon. And the idea is we know we're adding a hydrogen and a halogen, but beyond that, there is some order into which side does my halogen go on in my double bond. And so we're going to talk about that right now. So the rule is the halogen adds to the more substituted carbon. And with organic chemistry, this is where we're getting to, is we always want to understand why. And this is part of the reason why I like organic chemistry so much, is we have explanations for why things happen. And a lot of it you're going to see makes sense, and it builds off of what we've talked about before. And we're going to find out a lot of the time the answer has to do with stability. And so we've been spending a lot of time talking about stability. And so we're going to keep applying that. So I want to know, why does the halogen go on the more substituted carbon? And so to understand that, I need to look at the mechanism of this reaction. And this is part of the reason why we talk about mechanisms. It helps us understand why things occur. And when we look at this, the positive charge can go into one of two places. So remember, in the first step, we add our electrophile, our hydrogen, to our double bond. And so I will show you the full mechanism here in just a second. This is a partial mechanism. Right now we're explaining why does the halogen go on the more substituted carbon. I will show you the full mechanism that I expect you to know in just a second. But overall, when we add our hydrogen to our double bond, that hydrogen can go in one or two places. It can either go on this carbon or that carbon. And so this is the idea. If I add the hydrogen to the left-hand carbon, I make this molecule. So this hydrogen is the one that we've added. If I add the hydrogen to the right-hand carbon, we make this molecule. So this hydrogen is the one that we have added to our double bond. When I look at these two situations, I see that we both form a carbocation in both, but the carbocations are different. In this carbocation, this is a secondary carbocation. So you remember when we talked about primary, secondary, tertiary carbocations, it's the number of alkyl groups that are attached to the carbon that has the positive charge. So this one has 1, 2, so it's secondary. On the right-hand side, this one is tertiary. It's attached to 1, 2, 3 different carbons. So remember, these R groups represent, some carbons with hydrogens, and we'll see a more defined example here in just a second. But between these two, the hydrogen would rather go on the right-handed carbon here, which is the less substituted carbon. The reason why is it puts the positive charge on the more substituted carbon and forms a tertiary carbocation. So remember when we were talking about SN1 reactions, we discussed the stability of carbocations. More alkyl groups stabilize the carbocation. So remember, that had to do with hyperconjugation. We already explained that, but the rule is the more alkyl groups that I attach to the carbon that has the positive charge, the more stable the carbocation is. So between these two molecules, the one on the left, the one on the right produces a more stable carbocation. So this is the one that we are going to form in this step. So when we add a hydrogen and a halogen to our double bond, the hydrogen is going to go on the less substituted carbon. The halogen now, because it's going to attack our positive charge, is going to go on the more substituted carbon. And so we'll see some better defined examples of that. But why does it do this? Well, okay, because after the first step, we won't form a more stable carbocation. That's why the halogen goes on the more substituted carbon, because the hydrogen goes on the less substituted carbon. That puts the positive charge, our intermediate, that puts the positive charge on the more substituted carbon, and then that's the one that the halogen attacks. So the tertiary carbocation is preferred because we form a more stable carbocation, and then in the second step, when the halogen attacks, it's going to attack the the carbocation that is on the more substituted carbon. So when we look at the full mechanism of this, so this is the mechanism I actually expect you to know. That was just a piece of it. In the first step, we do electrophilic attack. So the electrons in the pi bond here, the second bond, the electrons attack an atom. Remember, bond attacking an atom forms a bond, so we end up forming this carbon-hydrogen bond. And during this reaction, we break the hydrogen-halogen bond. Remember, these electrons are going to jump onto the halogen. A bond attacking an atom forms lone pair electrons. So we end up forming X minus. So I should have had this species here is a product of this first step. We form X minus, or whatever halogen, like Br minus or Cl minus. These electrons are going to jump on there, and we're going to form a negative charge. So we have talked about halogens being a good nucleophile. They're a pretty good nucleophile. They have lone pair electrons and a negative charge. And in the second step, that halogen that we spat off during this first piece, so when the electrons jump onto the halogen, we're going to form a negatively charged halogen. We also form a carbocation. The halogen is going to attack that carbocation now. And then we when lone pair electrons attack an atom, we form a bond. So we form this carbon-halogen bond here. So this is the overall mechanism. It's only 2 steps, but this is the mechanism of the addition of HX to our double bond. So with this, when we talk about these reactions, you should try to remember what's the electrophile and what's the nucleophile. And that's pretty easy. That the arrow points at the electrophile. The arrow from the double bond points at the electrophile during electrophilic attack, and then during nucleophilic attack, the nucleophile attacks something, so we know that this is the nucleophile. So in the first step, the electrophile, you could say HX or just H+. That's really what's going on to my double bond there. That's the electrophile, and then the nucleophile is my X minus in this case. So you should always keep in mind what's the nucleophile and the electrophile. So this idea, so let's look at some real examples here. This idea that when we add to a double bond, my nucleophile goes on the carbon with the most alkyl substituents has a name. So here in organic chemistry, we're going to start naming certain ideas, reactions. So this idea that the nucleophile goes on the more substituted carbon is called Markovnikovs Rule. That basically means that my nucleophile goes on the more substituted carbon. And so we'll go through and look at some other reactions. And when we do additions to double bonds, that's one of our questions is, does it follow Markovnikovs Rule, or does it go against Markovnikovs Rule, which we'll find out later is called anti-Markovnikov. But right now, the addition of HX follows Markovnikovs Rule. So when I give you this reaction, so I have my double bond, I react it with HCl. In terms of going from reactants to products, I break the double bond. So there's two bonds in here, the sigma bond, the first bond, and the pi bond, the second bond. I break the pi bond, I form two single bonds from it. And then the question goes, well, what goes on those two single bonds? Okay, an H and a Cl. And then the idea is the Cl, the nucleophile, goes on the more substituted carbon. So I say, is there a more and less substituted side to this double bond? And the answer is yes. On this side, the left-hand carbon, there are no alkyl substituents. On the right-hand carbon, there is one alkyl substituent. So the right-hand carbon is the more substituted side, the left-hand carbon is the less substituted side. So I break the double bond, I form two single bonds. What goes on those single bonds? An H and a Cl. But I remember the Cl goes on the more substituted carbon. So when I look at this, sometimes it's a little hard to see the product, so let me map out what's going on. This is my first carbon here. That relates to this carbon. Here, this carbon is the one that gets the Cl, so it starts with this ethyl group, CH2CH3. It has a hydrogen, and then we're adding a Cl to it. So this carbon is this carbon right here. It has an ethyl group coming off of it. Well, that's this ethyl group. It has a hydrogen coming off of it. That's right here. And then we're adding a Cl to it, so we've added that. Remember, this carbon is this carbon in my product. It started off with two hydrogens, but we just added a hydrogen to it during this reaction. So that's why it goes from CH2 to CH3. So I broke the double bond, formed two single bonds. What goes on those single bonds? A hydrogen on this carbon and a chlorine on this carbon. So this is the idea. I don't really like, mixing things up, but it's important to know that Markovnikovs rule only comes about by a difference of alkyl substituents. So Markovnikovs rule doesn't really work if I don't have a more or less substituted side. So in this case with this molecule, if I was to do this addition of HX, I wouldn't have Markovnikovs rule in application. So I would make a mixture of products in this case. One with the chlorine going on this carbon, one with the chlorine going on the other carbon. That if I don't have a defined more or less substituted side, I end up making a mixture of products. So we try to avoid that in organic chemistry. But if you look at it, we end up making a mixture of the two molecules, one with the chlorine on one carbon, the other one with the chlorine going on the other carbon. So remember, it's still the same basic idea. Break the double bond, form two single bonds. What goes on there? An H and a Cl. But now I don't know which side gets the Cl, so they both go on there. And this is only true when I have an equal amount of alkyl substituents. So over here, the left carbon has one, the right carbon has one. Markovnikovs rule doesn't apply in this case. When that happens, I end up making a mixture of products. But if I do have a more or less substituted side, I make a defined product that follows Markovnikovs rule. So the next electrophilic addition that we make to double bond is the addition of water. And water in this case is going to be acting as our nucleophile. We'll see that a little bit more. But this reaction actually has a name. So when I add water to a double bond, it's called hydration. And so we're going to be reacting our double bond with water. And in this case, I need acid as a catalyst. So water is not a strong enough acid to actually do the electrophilic addition. That's why we're going to need H+. And water is going to act as our nucleophile in this case. So remember, neutral nucleophiles, like water, lose a hydrogen during the reaction. So instead of adding water, H2O, we lose a hydrogen and then we end up making OH. So we can convert our double bond into an alcohol. And then remember that we still follow Markovnikovs rule in this case, that our nucleophile, or water, which is going to eventually become an OH, goes on the more substituted carbon. So between these two, this one has one alkyl substituent. This one has two. So my OH in my product is going to go on the more substituted carbon in my double bond. So water is acid catalyzed, so we're beginning to see this. So by catalysis, it means we don't need a molar equivalent of H2SO4 or a strong acid. So if I have 1 mole of my double bond, I don't need 1 mole of H2SO4. I just need a small amount because my catalyst, so when we say catalyze, it means it's not being used up by the reaction. So if I only add a very small amount of H2SO4, so for these reactions, typically you add like 2 or 3 drops, and the acid is going to be recycled. We're going to put an acid in, or H plus, in the beginning, and then we're going to produce acid at the end. So we'll see when we look at the mechanism that the acid is not actually being used during this reaction. So remember our nucleophile, which was it's water, and then that's going to turn into an OH, follows Markovnikovs Rule, which means it goes on the more substituted carbon. So when we look at the mechanism, you need to realize, and we talked about this in 115b, when we acidify water, really it's not H plus floating around, really it's hydronium. So H3O plus is our acidic species. So when we add H2SO4 in water, the acidic part is going to be a hydronium, and so we're going to show that inside of our mechanism. So the first step is still electrophilic attack. So we've got to put our carbocation on there. And so our double bond attacks the hydrogen. This forms a bond between the hydrogen and our double bond. And remember, the electrophile goes on the less substituted carbon. So the less substituted carbon in this case is on the left. So this is where the hydrogen is going to go on here. So this carbon has 1 hydrogen. We add a hydrogen to it, and then in our intermediate here, our carbocation, we have 2 hydrogens coming off of it. After we form the carbocation, that's when we get nucleophilic attack. What is our nucleophile? Well, that's water in this case. So the lone pair electrons on water attack the carbocation. And then remember, when a neutral nucleophile does nucleophilic attack, we end up making this positively charged species. So we saw that back when we were doing SN1 reactions. And we don't like this positively charged oxygen, so the easiest way to get the positive charge off the oxygen is to move the positive charge to a hydrogen and deprotonate. And so the same thing is going to be true here. So remember, neutral nucleophiles lose a hydrogen, and in this case our nucleophile is water. It's neutral, so it's going to end up losing hydrogen. So just like when we were talking about substitution reactions, when we have a neutral nucleophile, generally the last step in the mechanism is a deprotonation. So after we do nucleophilic attack with a neutral nucleophile, we end up forming a positively charged oxygen. We want to get rid of that, so typically what we have is a deprotonation. So in this case, the most basic thing in there is water. So the lone pair electrons on water attack the hydrogen. We connect the bond between the lone pair electrons and a hydrogen here, and that's why we end up making H3O plus. So we got 2 hydrogens on our oxygen. We grab a third one to form hydronium, and in doing this, it deprotonates the hydrogen. So this is just an acid-base reaction that we saw in the very beginning here. The electrons on this OH bond move to the oxygen, and then we end up forming our OH inside of our product. So the idea is we put hydronium in the first step. So we used up our acid, but we make hydronium in the end. And that's what we mean by catalysis is during this reaction, the hydronium is not actually used up. It's put into the reaction in the beginning, it comes out at the end, so it's not actually used by this reaction, so we only need a relatively small amount. But we need that acid here to start this reaction. We needed the hydronium to do the first step, the electrophilic addition. That's why we needed to put acid inside of there. So remember, especially with additions to double bonds, you want to remember what the nucleophile is, because that nucleophile is the thing we use to track Markovnikovs Rule in this case. So when we look at an example of this one, I have my double bond. I'm reacting it with water and H2SO4. And you're going to see we're going to be talking about a lot of reactions that involve double bonds. And the fact that we're starting with a double bond doesn't really tell me that much. It's really the reagent that tells me what's going on. So when I react a double bond with water and a strong acid, typically it's going to be sulfuric acid, H2SO4. That tells me I'm doing a hydration. That tells me I'm adding water to the double bond. that tells me I'm going to be making an alcohol in this case. So the first thing I do is I say, does Markovnikovs rule apply? So with a hydration, it does. I then say, do I have a more and less substituted side of my double bond? Yes. So on the right-hand carbon, I have no alkyl substituents, no carbons coming off of it. On the left-hand side, I have 2 carbons coming off of it. So this is my more substituted carbon. In terms of this, and this is the way I think about the reaction. So this is different from the mechanism. So the mechanism is showing all the arrows. I like to think about things differently when I go from reactants to products, though. To go from reactants to products, what I do is I break this double bond, I form 2 single bonds, and then what goes on those 2 single bonds for a hydration is a hydrogen and an OH. And the OH in this case goes on the more substituted carbon. So here, this carbon in my reactant is this carbon in my product. And so the OH is going to go on that. So remember, water loses a hydrogen to become OH, and then the hydrogen goes on the less substituted carbon. So here, this carbon is this carbon over here. It started with 2 hydrogens. It's added a hydrogen to become CH3. So we break the double bond, we form 2 single bonds. What goes on those single bonds is a hydrogen and an OH, and that gives me my product in this case.